Good afternoon. Welcome for this presentation about software obfuscation using C11. Some word about me. My name is Sebastian Andrivet. I'm a cyber feminist activist and I have also jobs. I'm working for SCRT in Switzerland. I'm doing penetration testing and forensics, and I'm auditing mobile applications for SCRT. And I'm also working for ADV tools. I'm doing development for ADV tools. To simplify, I'm attacking with SCRT and I'm defending with ADV tools. So what is the problem? Why I'm talking about obfuscation? I will show you a small example. I will take a MDM application, MDM agent. MDM is a mobile device management system. It's a way to a company to control the security of mobile devices. For example, it can control if a device is jailbroken or not. And if it's jailbroken, it will not permit access to business emails or things like that. So I will take one of those MDM. I will open it in IDA. Okay. So no, it's not the right one. Sorry. Okay. So I open a MDM agent, so an application which is deployed on the mobile device, an iOS in this case. And I will try to find the jailbreak detection code. One way to do that is to look for strings. So this is a list of strings in the application. And I will look for Cydia. Cydia is the equivalent in the jailbreak community of the Apple App Store. So I just type in Cydia. And I found things interesting, including device jailbroken detection complete and things like that. If I look in the binary, I have my C string. And with IDA, it's possible to find cross-references, to find references to this string. Here we are. It's a CF string, an Objective-C string. And again, I will search for cross-references. And I found some occurrences and a method which is called isJailbroken with File Manager, a good candidate. And I have some code. I will use a decompiler to make it clearer. So apparently this function is filling an array with a list of strings with a black rain, which is a well-known, little bit old, but well-known jailbreak, etc., Cydia, etc. And if you look at the code, it's a little bit complicated because apparently they compile this agent with some profiling code, but it's not very difficult to understand. They just maybe it's not easy to see, but it's written file exists at pass. It just checks if the file exists or not. It iterates the array with this list of strings, and if it found one of those files, it assumes that the device is jailbroken. And to avoid this, to remove this, you just have to patch this function to return false at the beginning. You reassign the binary, you redeploy on your own device, and that's all. Your device will be compliant, but it will be jailbroken. And I wanted to make my own jailbreak library, jailbreak detection library, and this is exactly the situation I wanted to avoid. It's too easy to find it. Of course, it's only an example. Sometimes it's a little more complex, but most of the time it's like that. You just search for some strings, you find a function, you patch it, and that's all. So this is my motivation to do some obfuscation. What is obfuscation? I will take an example. I will take an application, and in my case, this application is Katy Perry. I will take an obfuscator O, and I will apply this obfuscator to my application Katy Perry, and I will see what I get. Do you have an idea? No? Yes? I get another Katy Perry. It's still Katy Perry. It has almost the same semantics, almost the same behavior. Perhaps it's a little bit slower, but it's still Katy Perry. It's an obfuscated Katy Perry. More formally, the obfuscation is a deliberate act of creating source or machine code difficult for a human to understand, for a human and not for a computer. I decided to implement my obfuscator with C++ because I was designing a library for iOS, and most of the time you write iOS code in Objective-C. And it's possible to mix Objective-C and C. It's called Objective-C++. Don't know what I have said. Of course, you understand. To explain how to use C++ to do my obfuscator, I need to explain a little bit C++ metaprogramming. And C++ metaprogramming is based on C++ templates. For example, in your application, you need a stack of objects. You have two methods, push and pop. And one way to implement this without C++ templates, it's like that. You declare a class, stack, with two methods, push and pop. And you have a parameter, an object, and it's the type of the object is a void star. It's a pointer to anything. And if you have a stack of singers, you can push Britney Spears onto the stack. And if you have another stack of apples, you can put a Macintosh. You can push a Macintosh. And both instances, both objects will share the same implementation, the same class. With C++ templates, it's different. You make small modifications. You declare a template with a type name called T in this case, and you replace the type void star by T. So now you have a stack of some precise type. And I still have my stack of singer, but this time it's explicit. You explicitly declare a stack of singer, and you can still push Britney Spears. And for my stack of Apple, I can put a Macintosh. But in this case, I will have two different implementations. Each object will use a different instance of the class. There is no code reuse in this case. It's possible to share some code, but by default, code is different. And thanks to that, you can make some optimization based on the type, on the template type. One important aspect of C++ templates is that you can achieve type safety. For example, if I try to put an apple in my stack of singers, I will have a compilation error, not a runtime error, a compilation error. In the first example, I can put any kind of object because it was a stack of anything. There are some exceptions if you try to put U2 into apples. Sometimes it's working, sometimes not. Just a joke. I don't know if it's funny or not. Like I said, with C++ templates, you can make optimization based on types. In the standard library, you have a method. It's a meta method, enable if, and with that, you can, for example, declare a class. The syntax is horrible. I will just explain a little bit. You have a member function in your class, and if the type T is a pointer, it will be enabled. If it's not a pointer, your class will not contain the method. So it's a way to not to generate code. You will generate different code based on types. And this is C++ metaprogramming. Instead of dealing with data, normal program manipulating, computing data, in this case, you are making computing on types. And based on that, you can generate different code. It's a subset of C++. It's Turing complete. It means that it's a full programming language. It's very close to functional programming. For example, you don't have variables. You have to use recursion or tricks like that. And it's part of the C++ standards. There are major enhancements in C++ programming in the latest versions of C++, C11 and 14. And now I will show you an application of that regarding obfuscation. In my demonstration at the beginning, you see that it's very easy to find strings. And what I want to do is to obfuscate strings. This is some requirement of my obfuscation. Of course, I can make obfuscation manually. I can modify the source code, perhaps I run a preprocessor or something like that, but it's not what I want to do. I still want my original string in my source code. When I'm debugging, I still need my original string because otherwise it's a nightmare to debug and to manage. If possible, I prefer developer-friendly syntax. And most important, in release builds, I don't want to see my original string. Okay, so let's make an implementation. I'm declaring a class. MetaString1 is declared as a struct, but it's almost the same as a class. And I have a constructor with one parameter, a pointer to a character. This is my original string. It's written const expression. It means that it's a method for the compiler. It has to be evaluated at compile time, not at runtime. No code will be generated for this method. And to store my obfuscated string, I need a buffer. So I'm declaring a buffer. It's an array. And I will fill my buffer with my obfuscated string. So the principle I take is I take each character one by one. I encrypt. It's not really an encryption, it's an obfuscation, but I call it encrypt. I encrypt each character and I initialize my array with these encrypted characters. In C++11, it's possible to, instead of declaring one template parameter, you can declare a list of parameters. It's called variadic templates. And you just put the type and 3 dots. And indexes, in this case, it's not one template parameter, it's a list of parameters. And the compiler will duplicate the code for each value in my list. So For example, if in indexes I have 0, 1, 2, it will generate this code. I also, in C11, you also have an operator says off with 3 dots. It gives you the length of the list indexes. And I put +1 to store the null byte at the end to terminate the string. And for my first implementation, I will use a very simple encryption, obfuscation. I just make a XOR with a hard-coded value, 55. And the decryption is exactly the same since it's a XOR. All the methods in blue are evaluated at compile time by the compiler. And of course, during the execution of my application, I need the original string, so I need to decrypt the string, so I'm declaring a decrypt method. The implementation is very simple. You just iterate each character. I call decrypt, and you can perhaps, for example, you can replace what you have in the buffer by the obfuscated string, and you return the buffer. So it's working, but I have a small problem with that. Yes, it's just a way to call it. I'm declaring a macro because this syntax is not very funny, and I'm preferring that. So you call it this way. My implementation has a small problem. The problem is that the list of indexes is hard-coded, like you see in the macro. And as a consequence, if I have more than 6 characters, it will be truncated. So I introduce a second version of my implementation. I will generate the list of indexes, 0 to a certain number, with metaprogramming. In C++14, there is a standard template for that, index sequence. But this version of C++ is very new. It's already well supported, but I prefer to be compatible with C++11, so I have implemented my own version of index sequence, very simplified. It's called makeindex, and this expression will generate a type indexes with as parameters 0, 1, etc. My list of indexes. So now in my macro, I can replace my hard-coded list here by makeindexes and with the length of the string. To call it, it's still the same, but this time it's not truncated. I still have one little problem. The key is hard-coded. So it's not difficult to make a script to try to brute force, or even to, it's always 5.5, so you just try every binary data in your application, and you try to brute force this and to extract the original string. And I wanted to have a different key for each compilation and a different key for each string. So I introduced a new parameter called k. And this key has to be generated randomly, or almost randomly. So I need some randomness at compile time. In C++11, you have a random header, but it's only for runtime, it's not for compile time. So I've written a small meta-random template. It's based on the linear congruential engine. It's not a uniform distribution because I'm using a modular operation, but it's not very important. I'm not doing cryptography. I'm doing obfuscation, and it's a recursive template. And I have something to generate a random number, but I need a seed for this engine. And it's something which is not so easy to find a seed at compile time. You have some macros in C and C++. You have, for example, time. It's the time of the compilation. It's the time in text, but it's not complicated to transform this into a number. But if I'm using only time, every string or almost everything string in my application will share the same key. Almost because the compilation may take some seconds. But what I want to have is really a different key for each string. So I'm using another macro which is called counter. It's not standard, it's not part of the standard, but it's well supported. It's supported by LLVM, Intel compilers, Microsoft, etc. And by combining time and counter, I'm able to generate a different key for each string and for each compilation. Okay, it's great, but is it possible to go even further? For example, to choose a different obfuscation algorithm for each string and for each compilation, and to choose this randomly. And yes, it's possible. I'm introducing a new parameter, A, for algorithm. And what is possible with C++ is to make what is called a partial specialization of a class. So you declare the class with this parameter, an int, and you say for 0, this is the implementation. And for 0, for example, I will use XOR. And for 1, I will use another implementation. And in this case, I will just add the key, etc., etc. You can make how many implementation you want. And again, I will reuse my meta-random to select randomly at compile time this value. And I will now show you the result. So I've written a small program with just this. This is without obfuscation, and this with obfuscation. Yes, it's big enough, I think. So this is without obfuscation. Of course, in the binary, you have the original string, and you see it's just making a call, nothing special. And if I look, maybe I can take, yeah, I can magnify. And this is my obfuscated, it's using my obfuscator. You see that each value, each character of the original string has been changed. And more interesting, you have a mix of move opcode, of move instruction with the value. The compiler has optimized the initialization of the buffer. In hexadecimal, you see this is the move and this is the value of the string. So in the binary, you don't have the original string and you don't have the obfuscated string. It's split into different pieces. And if you move at the end, This is the decryption, which is executed at runtime. In this case, it has selected XOR. You don't see a call because the compiler has decided that it's small enough to put it in line. What time is it? Okay. I will show you another application of those principles of this obfuscator. Sometimes I needed to obfuscate calls. For example, if I'm calling an API of the operating system to detect jailbreak or detect if a debugger is there or not, I wanted to protect this call against static analysis. And for that, I'm using finite state machines. It's a simple example of a finite state machine for that. The idea when I'm calling a function is to put some code, a lot of code, between the caller and the target, the callee. This is my call, and this is my actual call to the target. And I will run a finite state machine in between. To implement that, I'm using Boost Metastate Machine library. Boost is a C++ library, and with a lot of different things in that. And you have different implementation of finite state machines. What is interesting is that using this kind of construction with a MPL vector, I'm just declaring the state table of my finite state machine, and the compiler will generate at compile time a finite state machine. It's a vector, but it's not a runtime vector. It's a compile time vector. Here it's not types, it's not values, it's types. It's all this is only construction for the compiler, evaluated only during the compilation. There is no representation of that except the generated code. It's not like an array or something like that. And I will show you the result. This time I will not go into the details of the implementation because it's far more complex than the obfuscation of string. I will just show you the result. So this is my call without obfuscation, and with obfuscation I have something like that. You just put the name of the function as the first parameter of the obfuscated call macro. And you can also combine this with obfuscation of string if you have strings as parameters. And I will just show you the result. This is without obfuscation with my two parameters. And I don't have a call. In this case, it's a jump because the compiler has decided to optimize the call, and it has replaced this with a jump. And I will show you in IDA the result with obfuscation. No, it's not that. I've made a compilation with symbols, otherwise you don't see anything. And this is the code I have. The compiler has generated some code, and if I'm looking for for my function. The function I try to protect. In my example, it's called function to protect. And if I look for cross-references to this function, IDA is not able to find it. We see in the first example with IDA that IDA is able to compute references, cross-references, what you are calling and what is calling you. And in this case, with the obfuscator, it's not able to find it. So if you know the function, you don't know where it is called. And since finished state machine is executing, if you try to debug step by step, it will take a long time. Perhaps I can show you where it is called. The address. No. Right. This is my caller. And this is, all this is generated by the compiler. It iterates the finite state machine. But I can go even further. I can combine my finite state machine execution with something which is evaluated at runtime. For example, I can detect a debugger, and if a debugger is there, I will follow a different path in my finite state machine. This is just an example of a finite state machine, and if I see a debugger, I will go back from state 2 to state 1. And if there is no debugger, I will go to state 4. And I will effectively call my target here only from between state 4 and state 5. So if I go back to state 1, you see I'm going directly to state 5, and my target is not executed. I have a predicate. In this case, it's the detection of a debugger. I can make an if somewhere, but I prefer to obfuscate that to avoid if are very easy to patch. And instead of a if, I will make some computation on the result of this predicate, and I will take a different path based on that. In the example, I'm just checking if the counter is odd or not. So of course I have a if somewhere, but it's hidden in the execution of the finite state machine. I can go even further. Like I said just previously, IDA is smart enough to compute cross-references. So I have to obfuscate the address of my target. It's simple. I can make some computation with an offset, for example. And I can reuse my meta-random template to generate this offset randomly at compile time. Each time you compile your application, it will use a different offset, etc. It's very similar to the obfuscation of strings. For the predicate, I take the example of debugger detection, but it's only an example. I made a small implementation for Mac OS X and iOS, but you can imagine to detect virtual environment, to detect jailbreak, to detect what you want, to combine these different things, and to select also these different predicates randomly at runtime, and it's increasing the complexity of reverse engineering. Of course, I'm not pretending that it's the solution against reverse engineering. It's only an element of a global solution. Some word about compilers. To be able to use this obfuscator, you need a compiler which is C++11 or 14 compliant. It's a case of LLVM, including Apple One. It's also the case with versions of GCC with Intel, but unfortunately, it's not the case of Microsoft. Microsoft has a lot of problems supporting C++11. C++11 is a major version in the history of C++. They have changed a lot of things, but they are not far. I've not checked the latest community preview of the future version of C++, Visual Studio 14. There is just a small detail which is not working. And if they are able to support that, the obfuscator will be possible to use the obfuscator with almost any compiler. I've written a white paper about this with far more details, in particular regarding the finished state machines. It's on your DVD normally, and it's published on GitHub. If you have any question, if you want to discuss about this, this is my Twitter account with my email address. All the source code is available on GitHub on my account. It contains the obfuscator. It's in source code, of course. It's C++ templates. It's in header files. With some examples, you have the white paper, and it's a very permissive license. You can use it for anything, including commercial products. I will just show you what it looks like. So this is in the code which is published in GitHub. I've mixed the obfuscator itself and the demonstration. Demonstration is only in main, and you have different way to use the obfuscator with different steps. The different implementation. You see the encrypted 3, encrypted 4, exactly like I described during this presentation. And I have also some examples with finite state machine. And if I'm running this example, if I can magnify this, no, yes. I put some logs in the samples so you can see what happened. For example, you see that for this string, it has selected F5 for the key, and for exactly the same thing, the same string, another instance, it's 1, etc. And at the end, perhaps you don't see it. This is an example of my finished state machine with debugger detection. When I'm running inside Xcode, it's running under a debugger. So I don't see anything here. And if I look at the code, this is a function I wanted to protect, and it's supposed to to print out prism. And if instead of running it inside Xcode, I'm running it directly, so I have my application, my sample, DV obfuscator. And this time, it's written prism. And I also see that prism is obfuscated itself with this key. If you make a release version, of course, you don't have all the logs. Otherwise, it defeats obfuscation. Okay, thank you for your attention. And if you have questions, I will try to answer.